Yeah. I mean, that's why like grad school is kind of weird. Like I mean, all I did was make silicon and germanium compounds, and I just care about like weird bonds. Like it's weird because you're just looking at something so yeah specific. I was actually thinking about talking about that today. Yeah. Well, yes and no. Yeah. Yeah. So that's what I wanted to talk about.
I wanted to show you a cool thing I saw on Instagram. This is an old miner's helmet that uses calcium carbide as its light.
Oh, what?
You just pour little bits in there.
Water.
Hmm. That's how you turn it on. That's how you
Oh my god.
light it.
Just water drips. That is so funny. That would be cool to like play with in lab.
I know. I saw this at the beginning. It says like, "Oh, could you or would you use this?" And my answer was, "Yeah, I would use that.
Yeah,
I
for
wanna,
sure.
I wanna put that on my head." I don't even know. But yeah, look how bright they are too.
That's crazy. That's awesome.
I thought you would find that cool.
God.
Oh yeah, you can turn in homework.
Do you know how to use these calculators one?
Yeah.
So I don't know why, but like when I want to grab something, so it's just a basic equation like x squared. And I hit graph. Does it do anything? I've got the plot one turned on. I couldn't think of anything else that you're
it.
supposed to hit grab.
Oh, yeah. Invalid information. Trying to go
You have
back
to
to
hit enter.
so weird.
I don't know if I accidentally did something. I was wondering if I should just reset it completely.
Huh. That's weird. I gotta play with it after class. Oh yeah, you can just turn it there.
It's like something like for me, you know? Like a small store. Yeah. Everyone should be able to do that.
All right, let's go ahead and get started. Are there any questions before we get started? Housekeeping things? No, we're good on everything. If you're in the chat online, say hi, so I know you're there. And so again, we'll do about like an hour of lecture today, and then we'll do our quiz. So our quiz is just over last week, so sig figs and all that good stuff. Actually, but before we go into lecture, I wanted to bring up a couple of things that I saw with the homework and some topics that I missed from chapter 2. So let's look at the homework. And again, I don't normally check your homework, but I'm at least kind of trying to while I can. Welcome, welcome in the chat. And so I noticed a consistent error. And so one of the questions was convert 5.75 centimeters cubed into millimeters cubed. And so it starts off okay. So you have your centimeters cubed. And then, right, we can write our conversion factors. There's 10 millimeters in 1 centimeter. But what happens when we cube this? What do we need to do to our conversion factor? Yeah, so we got to cube this. And I saw a lot of people just cubing the units, but they didn't cube the 10. So you got to cube, right, the whole thing. So let me kind of rewrite this so this looks not squirrely. So, right, we have to cube the whole thing. Oh, I'm going to pull up my calculator. And so, right, we can plug that in. So 10 to the third then, millimeters cubed over, of course, 1 centimeter cubed equals, and so now the units can cancel, and we can plug it in, of course, 5.75, or we can do our mental math, so times 10 to the third, oops. And then we should get this answer, so 5,750 millimeters and cubed. So I saw different answers, like 57 or so. So same thing for 14. So I'll just point that out because it was a similar thing. So we had 8.21 inches squared into centimeters squared. And again, we just had to remember to square our conversion factor. So that's a common mistake. So don't feel bad if you did that. So centimeters over inches and square the whole thing to get our conversion. So times 2.54 squared. And so that gives us the answer. So rounding to 3 sig figs, so 53.0 centimeters squared. Oops. Questions about this? So just watch out for it, be aware. Again, good if you saw that. If not, just note it for the future. So don't forget that. You got to square, cube the whole thing. And so the other little topic that I didn't really talk about in enough detail was we didn't talk about the masses on the periodic table and where they came in from, so that was in your book. And so let's start with bromine. And so what do you notice about bromine? What's kind of odd about the mass here? Do you know anything about bromine? Like what isotopes it has, or what are isotopes? Let's start with that.
Isotopes are atoms with the same number of protons but different number of neutrons.
Perfect. So same number of protons, different neutrons. And so common ones that we see are like carbon-12, carbon-13, and carbon-14. And so, right, they all have 6 protons. And then this has 6 neutrons, 7 neutrons, and 8 neutrons. And does anyone know what these are used for, these isotopes?
Carbon dating?
Yeah, so carbon-14 is for carbon dating. And so this is really in a small abundance, so like less than 1%. Oops, I went the wrong way. Like less than 1% of the abundance of carbon is carbon-14. So yes, that's used for carbon dating. And only goes back so many thousands of years, since it has a half-life of about 5,000 years. And we'll talk about this when we do radioisotopes. But the other kind of funny thing is that we don't really know why isotopes exist. We kind of have some theories that it's some stability of ratio of your protons to the neutrons. As you get to like the heavier elements, you notice the balance gets even more off. But again, we can't quite explain it all with the phenomenon. And so, right, we can at least kind of tell, well, with carbon-14, with those 8 neutrons, that leads to some instability. Question in the chat, so I think you were asking about isotopes, but yeah, like I said, we don't know exactly and how they formed or why they formed, so there's different stability. And so carbon-13 is rare, so this is only 1%, and it is important though in chemistry, and so this is kind of going beyond, but there is an NMR technique called carbon-13, and so basically, because someone had asked that question, well, how do we look at our fraction and verify that it's pure? And so a lot of that, what an organic chemist would use, or organometallic, are either proton NMRs, which gives like a pretty picture, and then right after the proton NMR would be a carbon NMR, is super important. Of course, the trick in the carbon NMR is, well, you're only looking at 1% though of your sample. Right, you have your sample there, but it's really only 1% of it that you're measuring, because that's your abundance. So that makes it difficult spectroscopically, but NMRs get more and more powerful. So this is turned into like a couple of minute process. A proton NMR you can get in like less than a minute, really. And so then we have carbon-12. So this is, of course, the most abundant. It's about 99%. Well, let's go back to the mass on the periodic table, and what does that mean? And so I wanted to point out bromine, because bromine has no isotopes that are around 80. So we have a mass there that's like roughly 80, but bromine, it's also funny, because it has 2 isotopes, so bromine 79 and bromine 81. So these are just, again, their total masses. So we could figure out their number of neutrons. But what I wanted to point out is what this mass roughly is. And so again, the funny thing about bromine, it only has 2 isotopes. And so they're roughly in about 50% abundance each, so half and half. So that also makes it unique. But the mass on the periodic table then is just the average mass of all your isotopes. And so we can write out the formula formally. So pick a different color. So your average atomic mass, And again, this is from your periodic table. What this really is the sum then, and it's going to be mass of your first isotope. And if you were doing this normally or like on a test, they usually give you a more precise AMU value with a bunch of decimals that you would plug in, and then times your percent abundance, of course in a decimal form, right? And that would be of isotope 1. And then, of course, you add up all your isotopes, right? So plus mass of isotope 2 times your percent abundance. And, of course, right, just adding up all the different isotopes. So if you get really bored in lab, you can check out that chart of the nuclides that's posted way up high, and then you can knock yourself out just looking at all the different isotopes and all the abundances that are on there. But that's where the mass comes from. So roughly, again, for bromine, and these are just rough numbers, so we have 79 AMU times 50% plus 81 times 50% gives us, again, of course, I'm doing pretty rough numbers, so we get about 80 AMU from this calculation, which again matches there. So we would get that number, you know, if I use the more precise values and actual abundances, but that's the process. And then we should at least talk about ions in a formal sense. So what are ions? So charged particles, and do we know what the name for those special, because we can have positive charges and negative. So cation, right, everybody remembers because it's got a giant plus sign in the middle. So that's what we call our positive charges. And so we kind of were dancing on this on Tuesday where we were saying, well, there's some elements that make ionic compounds and they tend to give up electrons. And so we're kind of dancing around things, but getting there. And so again, we mentioned with this trend. And so later today in this lecture, we'll go through the electron configuration and really start to see more. Why is it 1+? What do we mean by NS1? And just keep digging deeper into really what this periodic table is telling us. And so excellent, I see chat's following along as well with our ions. And so then we have anion, that's a negatively charged particle. And right, this could be an atom, and later we'll look at our molecules are really polyatomic ions, but still marching there slowly. And so let's look at, and what's this other term? So it came up in your homework and also your reading questions. So isoelectronic. What does that mean? Same, well, maybe not charge. You want to say that a different way? Yeah, same amount of electrons. So same number of electrons. And so let's start with, let's look at this. So we have this symbol drawn out for 44 calcium with a 2+ charge. So let's just do this really quick. So protons, neutrons, and electrons. So how many? So take a minute or so. And chat, you can put your answers in the chat. So let's start off with, so how many protons do we have? Well, I heard different answers. So where do we get our proton number from? So right, that's just the atomic number. And so I see it in the chat, so they have 20 protons. And so right, we should have gotten 20 just from here. So 20 protons. And then how many neutrons do we have?
24.
So 24. And so again, we remember that our total mass of an atom is just protons plus neutrons. So 24 exactly. And then what do we get for electrons? So there's a couple of different ways to approach this.
18.
So 18, so how did you reason that out?
Well, if it has a 2 plus charge, then it has to be 2 less than the amount of protons. So 20 minus 2 is 18.
Exactly, so that's one way to see it. So right, start with the neutral. The neutral has to have the same number of electrons as protons. So you start with 20, but then, right, we said electrons are negative, so if it's a plus charge, you take away 2. The other way is you could, of course, formally set it up algebraically, right? So your total charge is equal to, and I think of protons plus electrons, but then, right, electrons are negative, so I always put like a big fat negative sign in front of that. So that's how I think about it. So you're adding, right, 20 minus 18 really gives you 2 plus, or you could have set up the algebra, right, 2 equals 20 minus your x, and then solve from there. So let's pick then, and so I'll give people some time. So the name an ion or atom that's isoelectronic then to that, the calcium 44, 2 plus we just did. So what does that mean? We defined it. Do you want to give, so what's your idea?
I got one that was potassium cation plus 1.
So potassium plus 1, and so you said, and we can look, we'll double check. So that sounds right. So potassium, right, is 19, but if it's missing electrons, now it has 18 electrons, so that would be isoelectronic. Other options we could pick. What else?
Argon.
So argon is isoelectronic, and so of course that's neutral. Other ions. Yeah, chlorine minus 1. Any other ones we want to put down?
Would sulfur minus 2 also be isoelectronic?
Yep. And so, right, let's double check that. So sulfur, 16, of course, and then negative 2 brings that to argon. And we could keep going crazy, but any other last thoughts from probably chapters 2? Anything I skipped over? So I apologize. I don't really like how your book structures things, but that's also kind of the nature of starting to learn chemistry. There's like a lot of information, and it's also like a new language, right? So you're learning all these weird symbols and whatever they're trying to communicate. So I know it can feel hodgepodgey, and then kind of looking at your textbook, right, chapter 3 can feel all over the place. Your textbook is a great resource, but it's also very dense, so you might have gotten that. And so just, again, ask questions, and we'll try to hit kind of the big points and highlights in lecture to solidify things. All right, so we had started, just as a recap, so we talked about our alkaline metals and our alkaline earth metals, and we're at least kind of getting to these charges. And so then we want to practice our electron configuration, and then also translating this electron configuration, right, to Lewis dot structures and geometry, because really this is super powerful, what the information we're getting from the electron configuration. And so we'll do that. So let's back up for a second. And so let's start back at hydrogen. And so at hydrogen, and I would mark this on your periodic table. So this starts, right, our 1s orbital. And these are just our energy levels. And so we're kind of going to talk about electron configuration, mention s, p, and d orbitals. Then we're going to take a step back as we move forward and look at like electromagnetism, photons, and really studying elementary transitions. And then later, I think second quarter, we'll kind of go back to the MO theory. So again, just kind of hang with me. But this is a nice p-table, periodic table resource to look at. So it's just ptable.com. And then I've clicked over to the electron tab. And so this is nice because it has all these energy levels here, and it's going to show how to fill it up so you can double check yourself. And so again, we're just starting. So notice it has all this as the S block. And so you might want to go over to your periodic table and highlight this as the S block. And so obviously it gets awkward, so you have to remember, right, helium's a little special, and we'll talk about helium as we go right now. So explicitly, again, you might already know this, but we'll go through this. So our electron configuration, so we'll start with hydrogen. And so it's just 1s1. And so again, later we'll go back and put our quantum numbers with that, but we'll go back. So right now we're just 1s1, and we could also compare this to maybe like high school chemistry. So maybe you have seen this like n equals 1, and we have 2 electrons. And then the next level, right, n equals 2 is 8. Do y'all know what I'm talking about?
Yes,
So,
with the shells.
yeah, so this is what I called like our oversimplified picture right now. So we're going to take a lot deeper view into what all these orbitals truly are, but this is just kind of our oversimplified onion model. And so we'll tease out these numbers as we go. But really this first energy level, so all this contains is the s orbital. We'll get to kind of y later. So again, just hang with me, but it's really just quantum mechanics. And these s orbitals just look like little circles, and they can fit. And so the other way to draw it out is, so sometimes you'll see 1s, and so we just have a little line here for our s suborbital. And so this line just means that there's 1s orbital. Again, it looks like this for our 1s. And then it can fit 2 electrons in there. And so again, formally, we could write it like this for hydrogen, or, I could put it upside down. It doesn't really matter. We don't know what position it's in, just that there is 1. And so from that, if we march on over to helium, so of course now helium is 1s2. And so this is where we get the duet rule and why helium is a noble gas and considered unreactive. So its energy level, so 1s, so it has two of them. So this is filled. And so now we can say, right, satisfied by the duet rule. And so, of course, right, hydrogen also would follow the duet rule, but this is kind of an aside, so this is why, kind of why it wants to bond with itself. Again, we'll take a deeper understanding of this as we progress. So this is kind of our really sketchy back of the envelope, just kind of drawing connectivity. So continuing on, so let's go back. Yeah, questions?
Can we actually look at carbons orbitals and how that works out? Like with the 1s, 2s?
Yeah, so we're getting
Okay.
there. And so next, so your book, let's focus on the P block next. So we'll fill up P block. And so again, let's just go in order. So we're here at the 1s. Now we start our second principal shell of our 2s. And so let's just do beryllium so we're on the same page really quickly. So beryllium 1s2, 2s2. Okay. So again, we're getting a hint. And again, just so we're all on the same page, so these would be considered our core electrons. And so these would be centered on the atom itself, so they're core, they're non-bonding. And then these valence electrons, though, so whatever your outer ones, those are the ones that are going to be doing the action primarily. So then we said, well, let's start our P block. And so let's highlight our P block here. And so this is, and so let's at least talk about P orbitals a little bit. Again, I'm not trying to go too crazy right now. But for P orbitals, we at least want to know that there are 3 of them. So again, we'll see them again. And so I'm just going to call them, so normally PZ is your principal rotation axis, so whichever has the highest rotational symmetry. And then PX I'm formally doing in the XY plane. And then PY goes in and out of the plane of the board. So there are 3 of them, so sometimes you see them drawn like so. And if they're drawn in the same row, this means they are degenerate, aka same energy. And so this is where you start invoking, you probably have heard it called like the candy rule, right? Where like every side gets a little electron, but we'll get there. And so now let's mark this as our 2p. And so you could also kind of write this pattern here. So now we start, right, NP1, NP2, NP3, right, 4, 5, 6. So write that, if you need, but otherwise we can start seeing, well, this is why they have similar reactivities. They have the same number of valence electrons. We can see that with their electron configuration. All right, so there's a request for carbon. So let's do carbon's electron configuration. Does someone want to give me carbon's electron configuration? So then how would we write it though in like this format?
1p, 2p, 4.
We don't want to say
Would
one.
it be 2s2 and then 2p4? 2p2.
Yeah, 2p2, but then we need to start with 1s2. So again, right, just fill it up from the top. Oops, where's my? So you always start from, right, your first one, so you always have to start with the 1s first. And then notice, right, you do not have p orbitals in that first energy level. So that's what your little, that's what this is reminding you, is you can only have a 1s. And then once you get down to the second energy level, then you can have 2s, 2p exist. And then we'll keep kind of going. And so this is where some patterns occur. And so let's talk more about carbon and why this is weird. Because right now it looks pretty unassuming. So right, we have our core electrons. Yeah. So we could abbreviate to the previous noble gas. So in this case, it doesn't save us too much pen ink, but it would be appropriate to go helium then 2s2 2p2, since helium's right electron configuration is that. And as we get to the higher elements, we can just go back to the previous noble gas. Like once we get to tellurium, we can start with krypton in those little bracket notation. And that signifies everything from it. But we'll practice as we do this. Does that clarify? Yeah, so all this means is, right, the electron configuration to that point. But we'll keep practicing. So let's rewrite this in another way, because your book will all show this in different ways. Different resources will show this differently. And so we can write out, right, our 2p. So this is our highest energy level, 2s and 1s. And so again, you always start from your lowest energy level. So we have to put in all of our 6 electrons. So starting with our 1s, so 1, 2, 3, 4. And so this is where you get the candy rule. So we can't just fill up, right, 2 in the p. And so why that is you have to pay a price to pair. So that's not energetically favorable if there's a degenerate, aka same energy level available. So it's not going to do that.
Is this because electrons like to stay like away from each other because they're the same charge?
Yeah, but then, like I said, it's an energy price to then do one spin up, one spin down, because there's a little bit of repulsion there. So that's, yeah, so they don't, yeah, they want to
So
be,
they prefer to be in different orbitals?
yeah,
Okay.
yeah,
If they
before,
have to, then they'll just spin in opposite directions?
yeah, so then they'll formally pair up. And so with that, we can now translate this to what I call our Lewis dot structure. Except carbon is an exception. Oops. So let's go back to carbon. Well, let's instead go to one that does kind of behave better. And so this is already teasing why we're carbon-based life form, why there is a whole field of organic chemistry and not silicon chemistry. So silicon, it's now we've jumped around, but let me help you guys. So we were at the 2p. Now we continue on. So now we're at our next main energy level. So this starts 3s. So we fill that up. Now we're back to 3p over here. And so, of course, silicon's going to follow that similar pattern, right, of NP2. And let's write the electron configuration. And so I said we can start at the previous noble gas. So let's do that so we don't have to write 1s2, 2s2, 2p6. So that brings us to neon. So now we're at neon. And then we can continue, so I'll just go back up again for clarity. So we're at 10, now we go 11. So next energy level is 3s2, and then that brings us to 3p2. And so let's translate this to what a Lewis dot structure is. And so again, I'll rewrite it because I like this form. It helps us. So I'm going to ignore the core electrons now, so I'm only writing out these valence ones. So 2 in the S, 2 in the P. And so I'm not sure how y'all learned how to do Lewis dot structures before. There are usually some oversimplified methods to it, but this is why I like basing it off of the electron configuration. And what I say is, so we have our silicon here, and we have, 4 sides. And so usually you're told something like, oh, just, put an electron on each side and go around. But that doesn't have, meaning to the electron configuration. So we want to write this. So basically treat one of these as a side, and it doesn't matter which is which. So I'm going to put 2 electrons on one side for my 3s, and then put another 2 for my additional p's. And so this would be our proper Lewis dot structure. And so this would hold true for the rest of the elements. So, germanium would look like that. And I blanked on who's below germanium. And tin. And so again, the powerful thing too about this Lewis dot structure is it's reflective of its reactivity. And so especially like germanium, they can be isolated as these weird divalent species, and then they can also go on to do cool things because they have these 2 electrons that can donate to metals. But let's go back to carbon. So that was the rest of group 4. But, oops, we mentioned carbon was the exception. And so what can anybody tell me about carbon? Why do you think it's probably an exception? So it's weird. So it has 6 valence electrons, or not 6 valence, 4. So 6 total, 4 valence. But what else about carbon? Why is it cool?
It can lose all of its valence electrons and also gain 4 extra electrons to fill out all of the areas so that each electron has a pair.
Kind of. Basically, we'll say that carbon likes to hybridize. And so there's a lot of other things we can say with this. So hybridization. So that's the main key word. And so because of that, I drew it like this. But we could also say it likes to make 4 bonds. Carbon can also bond to itself in weird ways. So carbon triple bonds. It can make rings, so like benzene rings. And so silicon does not do the same. It does not hybridize in the same way. It does not do this as readily. And so people have, of course, been trying and exploring with silicon, but it does not behave that way. And so part of the reason, so carbon is also a lot smaller than you would expect. So we'll look at that later with our periodic trends that are coming up. But we can predict, our radius just based off the electrons and how they fill in the shell. But carbon is just smaller than the trend predicts. So because it's smaller, it seems to make these multiple bonds, and of course it also makes bonds with oxygen, nitrogen, phosphorus pretty readily. You know, obviously we're carbon-based life forms, but that's why there's so many, is because it can make all these double, triple bonds with other elements. And it does so in a way that,
Does that mean that it takes an electron from one of its lower orbitals and brings it to one of the higher orbitals?
so what happens, to not get too much into it, but, so it's called like mixing, but we'll look at it later. So basically you have the S and a bunch of P's. And so if you mix them all mathematically like this, you'll get a tetrahedral shape. So then this is what makes methane. So this is kind of going all over the place. But you can also mix just like 2 or 3 orbitals, and that gives you different pictures that make it have different bonding. But we'll get into this later, but that's at least kind of a little preview that carbon does really weird mixing with these orbitals. And I just take the pictures, so obviously there's like mathematical computation behind this. So you could do this mathematically. We're not going to go there. We just kind of appreciate the pictures. We put the pictures together. That's what they look like. And so, sorry, seeing a question in the chat. So they're asking about, so if we see just 2 dots, yes, this probably implies just the s orbital, and then other ones would be filled in with the p. But yeah, we always fill in like the s first, and then fill in, of course, the p's. So let's regroup for a second. And so let's, I know we're starting to run out of time. Let's see if we can skip over to arsenic, but let me help you guys. So we're over at 3p. So we fill this up, right, 3p6. Now we start our 4th main energy level. And so this is where things start to get tricky. So we have 4s, but then remember our 3rd energy level here, where, well, there were supposed to be 18 guys in there. And that's because we have a 3s, 3p, and now we have a 3d is allowed, but we didn't get there yet. And so 3d is actually here. So write that there to remind you.
Is it the whole of the transition metals?
Yeah, so now the whole transition metals, and so we could label this as our D block. So highlight this. So this starts our whole D block here. And then your book alludes to some weird behavior. We'll kind of touch on that. Probably not today, probably looking like Tuesday. But I do want to go back and talk about some oddities and give you some reason. But then we'll fill in the D's. And so quick D lesson. So I won't show you the pictures right now, but let's just take a quick understanding. So there are 5 D orbitals. And then each one of those suborbitals can hold 2 electrons again. Sanity check, that means that this should be 10 across. It is, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that matches with our D's. And then after 3D, we go back to 4P. So note that for yourself. And so let's practice arsenic's electron configuration. So give yourself a few minutes to do that. And if you're feeling up for it, translate that to your Lewis dot structure, because that's going to be powerful. Oops. Let's see, do we have answers? Are we ready or still thinking? What do we get for arsenic? Wait, that's not arsenic. Does someone want to give us arsenic's electron configuration, or at least start us off?
I can try.
Yeah, go for it.
So I started with argon as my starting bit, and then I did 4s2, 3d10, and 4p3.
That sounds good. Is that what everybody else got? Looking for a thumbs up. I see lots of thumbs up, so that's good. And so a note for these arsenic ones. And so again, we're kind of running out of time, so we'll go back to the transition metals. But notice, so right, we have all these transition metals, but once you end up back on this side in the p block, we pretty much ignore the d electrons, right? So we don't consider them valence electrons like for arsenic. So we just say, right, it follows a pattern of 5 valence electrons. So it's just not generally invoked in bonding.
So would the Lewis dot structure only have 3 dots then?
It should be 5 because the 3, the P, and then we still look at the S.
Oh, okay.
Yeah, so those, and that's where it gets weird. So that's only when you cross over to that P block that these are your valence electrons. So those are the ones that tend to mix then and participate in bonding. So primarily your p orbitals. And so let's translate that. So that means arsenic. And we'll do 2 on one side, filling up, right, our 4s2. We're going to ignore those 10 d electrons, and then we'll put 1 in each p, just like that. Yeah.
Question about the D block. How exactly does that work?
Number. You know what I mean? Like how the rest go, like one S, two S, three S, four S, and like
So this would be, right, 3D1, 3D2. But then why I didn't really want to talk about this is because we're going to look at some exceptions. And so we'll talk about what we would expect it to fill as, but then we're going to start looking at some of the weird behavior. So we're going to save those thoughts for Tuesday, and then we'll go back and practice some electron configuration of these transition metals. So last final thoughts. I know we're like at the time limit here, But other powerful things that I wanted to show you. So this is giving us a lot of information. Again, this is going to be, right, your group 5 Lewis dot structures. They're all going to start looking like that. So I'm just going to draw phosphorus real quick. Right, looks the same. But this is also telling us about bonding. So if it has these 3 lone little electrons there, well, that's showing us it wants 3 bonds. And we'll see that. And so using phosphorus, just because I'm more familiar with phosphorus, but again, arsenic would behave similarly. So we can have like this compound, and we're going to see, right, well, we know the geometry as well from this. Again, we'll get there, but we're getting a lot of information. But this also tells us, well, this is probably still reactive because it has these 2 electrons here. So not only do we see that we have, right, this phosphorus trichloride, but then we can predict that it's going to be reactive, and then we find that it is reactive. So if you work with phosphorus trichloride, it's going to be an angry fuming powder because it wants to bond with oxygen. So then it'll probably make some oxygen bonds, again, from that reactivity that you would predict. So that's just a preview of kind of where we're going. And so, again, we'll have to stop here. And then so on Tuesday, so we're running a little behind schedule, but that's fine. Because this is important to at least build a really good foundation of what the heck does this all mean in terms of like our orbitals and then in terms of reactivity. So then we'll go back and look at the transition metals and then practice a few more of these weird ones and continue our electron configuration discussion. All right, take a 10-minute break and then we'll do our quiz. And I will hang out for a minute or 2 on stream just in case there are questions. And yeah, if you want to take the quiz at home, you can just email me, but otherwise you can make it up in class.
So I got just about everything we were talking about except this part. So that look right for?
Yep, so then 4P, 3D, so 1, 2, 3, 4. I think you're just missing a line because there should be 5Ds, but yeah, that's, and so if you want to check yourself, right, because it's a lot. Yeah, go in that P table, and what element were we just doing? Yeah, so I have arsenic selected, and so you can double check and translate. But
And is it just ones all across, like?
yeah, well, they're little half arrows.
Oh, half arrows.
Yeah,
Okay.
and that'll go back to like the quantum numbers, but we're marching there slowly. So yeah, putting the pieces together.
So I can take the quiz at home?
Or
I'll probably just take it, yeah.
yeah, if you need to get going, I'll hand it to you.
I'll
so you can get it
just
10
like do
minutes.
this outside and then I'll give it back to you.
Yeah.
I don't know what
Okay. Yeah, I'm trying to go. Yeah.
And can we use our notes on the quiz?
Yeah. So yeah, it's open note quiz. So you can get your notes.
Did you receive the ICC one in your email?
I did. Yeah.
Just wanted to make sure everybody's getting it.
I got scared for a second. I got so many emails.
Yeah. AHG has been a lot. I have been spending hours every night after my 6 p.m. get home time.
I believe it.